Now this one has quite a lot in it, which is why I left it to a separate video of its own. And so we're taking d by dx of this thing here. Okay, now that's the equivalent of saying find dy by dx for y equals that thing. So now we have to take the derivative of that, and you can see that it's composed of two parts multiplied together, this bit and this bit. So it is a product rule. But there are a couple of things we need to know before we do this. First of all, you'll notice that there's a square root there. It's a square root of something to the power of 7, and we have to change that to a half power. Now, what I mean by that is, if you have, say, the square root of x, that's the same as x to the power of a half. Hopefully you should remember that from before. If not, let me know. If you had x to the 7th square rooted, that's the same as x to the 7th to the power of a half, the half power being the square root. And the rule of indices for this is you're allowed to multiply these together, so we get x to the power 7 over 2. Now, in theory, you could write this as x to the 3.5, but in general, mathematicians, physicists, and engineers do not write analytical fractions as decimals. They tend to write them as fractions like 7 over 2. So 7 times a half can be written as 7 over 2. So that means that this problem on the previous page here, 3x plus 5 to the power 7, can be written as 3x plus 5 to the 7 over 2. So we're going to need to use that. So I'll go back and I'll fill that in. Okay, now the next bit, it's not obvious yet, but we're going to have to do some factorization at the end of this problem. And I just want to talk a wee bit about factorization techniques, because I think if I don't do that now, I could cause a bit of confusion later. So let's go forward a couple of pages and look at factorization. So let's say we've got ax squared plus bx squared, and we want to factorize that out. Now you'll notice that this x squared here and this x squared here are in both terms, so I can take that out, both of them out, write it at the front once, and then write what's left, a plus b. And that's it factorized. Now we know that this is the correct answer, because if we multiply that by that, multiply the brackets out again, multiply that by that, I get ax squared, and if I multiply that by that, I get bx squared, which is back to where we started, so that's correct. Now, we can also factorize in stages, so let's say we had 4ax squared plus b, well, it's 8bx squared. You'll see the x squared is in both of these, so I can write it at the front once and write what's left in the brackets, 4a plus 8b. And both of these are divisible by 4. Now what I'm going to do here, and I think this is probably conceptually easier than breaking this into 4 times 2 and taking 4 out as a common factor, is to say, well, look, I can divide that whole term by 2 as long as I compensate by multiplying that one by 2. So as long as you do the opposite to both parts, the problem will remain the same, as taking any number like 3 and multiplying it by 2 and then dividing by 2, you still get back to 3. It's the same here. I can divide that by 2. That will leave me with 2a plus 4b, dividing both parts by 2, as long as I multiply that by 2 as well. And that's taken the common factor out. Now, you'll notice here, this is also, each of these numbers here is divisible by 2 again. So I can take that out, multiply by 2 on that side. So that gives me 4x squared, 2 times 2. And then over here, I get a plus 2b. Now, there's no other common factor there, so that's it. Now, I could have gone straight from here to here if I'd spotted that they had a common factor of 4. Now, it's not entirely unobvious that these both divide by 4. So if I do divide by 4, multiply by 4, it gives me 4x squared a plus 2b, straight to the same answer as that. The reason I did it in bits is because it's often hard to see the highest common factor. This 4 here is the highest common factor of these two terms, and sometimes that can be difficult to see if the numbers are awkward. So what I'm trying to say here is you can take bits out a little bit at a time. You don't have to take the whole highest common factor out in one go. So let's have a look at another one. Let's say you had bx cubed. Right, so now I've got ax squared plus bx cubed. We can see here we've got an x squared and an x cubed in each term. Now it's not entirely obvious looking at that these are the same thing, but what you potentially could do is you could say, well, that's x squared plus b x times x squared, and now because x times x squared is x cubed, you can take x squared out as a common factor, leaving a plus bx. Now, using my division method, plus bx cubed, we'll do this again over here, you can see that both of these are divisible by x squared. So if I divide that by x squared, I'll need to multiply by x squared as well to compensate. Now, I'm going to create an x squared term here, and if I divide that by x squared, I get a, and if I divide that by x squared, I get bx. So you can see that by dividing by this and multiplying by that, I can factorize it out in the simplest possible form. Now, the reason I would do this, well, you could leave the problem like this, or you could write it like this, and it depends, ultimately it depends what you're going to do next in your calculation. So if you're going to add and subtract a term, you might leave it like that because potentially you might subtract ax squared and it would cancel with that, simplify. Or if you're going to multiply or divide a term, you would leave it like this because you might get cancellation with that x squared. So both of these forms have merit. Maybe I'll write that out actually just to show you. So it's not part of the factorization, but if I had ax squared plus bx cubed, and then the next part of the calculation was subtract ax squared, then that would cancel out with that and leave bx cubed, which would be much simpler. So if you're going to add or subtract, you probably want to leave it in this form because then it will be obvious that you can erase terms. If you'd written it like x squared a plus bx, oops, and then subtracted ax squared, it's not so obvious that you're going to get that cancellation. However, if your problem was looking like this, okay, and the next step was to divide by x squared, then these would cancel out and leave a plus bx, and it's obvious that that's going to happen, so you get that simplification. If you'd left it as ax squared plus bx cubed and divided by x squared, yes, you could cancel that and that, but it's not quite so obvious. So it's probably worth, and indeed there are marks for factorization in these problems, so you want to try and factorize them out as much as possible. Now, let's look at a slightly more awkward example. Let's say you had ax to the 3 over 2 plus bx to the 5 over 2. Now, again, it doesn't look like these are going to factorize, but both of these are actually divisible by x to the 3 over 2, as long as you compensate by doing that. So if you've got two fractional powers here, you can, or two powers of any kind here, you can factorize out the smaller one now. 3 over 2 is smaller because that's 1.5. 5 over 2 is 2.5, that's the larger one. And you can see why that's going to happen, because if you divide this by x to the 3 over 2, you're going to get left with a. And if you divide x to the 5 over 2 over x to the 3 over 2, that gives you x to the 5 over 2 minus 3 over 2, subtracting the indices when you divide. And when you do this, you get x to the 2 over 2, or just x to the 1, or x. And you can do that in a calculator if you're not confident with fraction arithmetic. If you use your fraction key to do 5 over 2 minus 3 over 2, it will say the answer is 1, so you just get x. So this will come out as a plus bx but of course I have to multiply by x to the 3 over 2 as well. So here I've factorized out the x to the 3 over 2. Now I can check by multiplying out that we get back to where we started. So if I try and multiply that out, I get ax to the 3 over 2 plus bx times x to the 3 over 2. Now remember that it's x to the 1. So when we combine these, x to the 1 times x to the 3 over 2, that's x to the 1 plus 3 over 2. And again, that's x to the 5 over 2. And if you're not confident about doing that arithmetic in your head, you can use your calculator. So that comes out as ax to the 3 over 2 plus bx to the 5 over 2. Now, oh, shudder. Okay, so by factorizing out these awkward things, it can get quite messy. So let's have a look at another one, this time with several terms. So let's say we have 4a squared x to the 7 over 3 plus 8b a x to the 4th. Now, this one is going to be messy. Okay, we have to accept that. So first of all, I notice that I can divide both of these, divide by 4, as long as I multiply by 4 at the end. So that's going to give me 4 bracket a squared x to the 7 over 3 plus 2b a x to the 4th. So remember, 4 divided by 4 is 1, so there's an implicit 1 there, but you don't write it when it's a chain of products. And 8 over 4 is 2. So now we can look at this and we can go, right, well, I'm going to divide both of these by a to get rid of this a and remove 1 from there, as long as I multiply it by a there. So I get 4a, and that leaves me, well, a squared over a is just a, x to the 7 over 3, plus 2b x to the 4th. So now there's no b in both terms. There's a b there, but there isn't one there, so we can't factorize that out. The only other thing we can get is the x's. So I am going to factorize out the smaller term. Now, 7 over 3 is a smaller number than 4. 7 over 3 is actually 2.333. So I'm going to divide both terms by x to the 7 over 3, as long as I multiply by x to the 7 over 3 there. So that gives me 4ax to the 7 over 3. Then that will cancel with that, leaving just a. And then 2b x to the, well, that's going to be 4 minus 7 over 3, because you're doing that divided by that. So the power is going to subtract using the laws of indices. 4 minus 7 over 3. Now you can do that in your calculator, or I can do it by cross multiplication. So I'll do 4 times 3 is 12, minus 7 over 3 is 5 over 3. So we can write that as 4a to x to the 7 over 3, a plus 2b x to the 5 over 3. Now, in some respects, you could argue that this last term actually looks more complicated than this term here. So we could have, bearing in mind we could have stopped there, because this has 1 fractional power, but this has 2 fractional powers. But the advantage of this expression is, because we factorized it out, if the next process in calculation was, say, a division by something with x, we'd be able to see the cancellation immediately. Anyway, regardless of that, this is the technique that I use for factorizing out problems with nasty fractions. So it might take you a bit of time to work through that. Have a look through this again if you're not 100% sure. Stop the video, go back, have a look, and then let me know if you're stuck. We're going to use this technique in our previous problem, which is this one here. So after all that,